Thank you for coming, everyone. I'm Jacob, a senior software engineer and a team lead at HyperConnect.
And I'm Gihoon.
In this session, we'll introduce how we redesign the matchmaking system of one of our service, Azure, and Flink framework, and how we overcome the challenges. I will divide this session into 4 parts: motivation, matchmaking architecture, infrastructure, and lastly, I will introduce our stateful matchmaking system. Let me give you some background about the company, HyperConnect, and the service, Azure. HyperConnect is a video and AI company that was founded in 2014 and offers multiple services such as Azure and Hakuna. Azure is a video chat application and is a great place to connect with people with various backgrounds. To meet others, the user will swipe left on the live video screen. We call this a discovery. In Azure, more than 180 million discoveries are happening in any given day. Our team is developing and maintaining the matchmaking system for Azure. And there are 3 motivations why we redesigned the matchmaking server with Flink. The first one is scalability. During the peak time, our matchmaking system handles more than 5,000 requests per second. That means the system should work with 12 million candidates per second to make the optimal result. Next is stability. Our matchmaking system is the core of the service. So the response time and the uptime of the system directly affect to the business. These constraints make it more difficult to implement new features for the legacy system. And the last one is stateful matchmaking. We've come to understand that to improve the matching quality, it was essential to keep some state for each users. But previously, with a stateless matchmaking system, we adapt an indirect approach, such as attaching the event processing pipeline around the matchmaking system. These approaches had limitations on latency and complexity. So we decided to redesign the new matchmaking system from the ground up. And there are 3 strong reasons why we choose a Flink framework for our new system. The most important one is the capability for low latency iteration. Flink supports implementing the kind of feedback system having the processing cycle under a second. With the iterative stream and functionality flexibility, we can easily migrate the matchmaking system. And next is operator-based loosely coupled architecture. To improve the quality of the results, the new matchmaking system should explore more potential candidates pairs with multiple scores. And of course, some of them may not return responses in time for various reasons. With the async data stream, we can implement the loosely coupled architecture running stable, even though some of the scores are not responsive. Last is intrinsic support for state management. To deliver more value to our users, it's needed to implement the real-time inference, and as a source, it's needed to manage the state in real time. For this purpose, it's required to include the state management into the matchmaking system. And Flink's intrinsic state management function and better memory management architecture helped us to implement the stateful matchmaking system and run stably. So for the next part, I will turn it over to Gihoon to explain the architecture of the matchmaking system.
Okay. Hi, I'm Gihoon, and I'm developing a matchmaking system as a software engineer with Jaehyeuk Oh. Let me introduce you step by step how matchmaking is done on the HyperConnect and how it is implemented. First, what is matchmaking? Traditional matchmaking is the process of matching 2 or more people together. We aim to collect match requests from the specific unit of the window and select the best pair among them. For real-time matchmaking, it is more difficult because of time constraints. We must complete the matching cycle in a short, limited time. So we need low latency application with large computations. To implement the matchmaking on the Apache Flink, we will separate the process into 6 steps. There are general 6 components in matchmaking steps: collect source, feature engineering, pair generation, scoring, pair aggregation that code matchmaker, and after these 5 steps, matchmaking result goes to various sinks. On the other hand, leftover goes to pair generator and repeat 3 to 5 steps again. It makes matching stream cycle. In pair generator step and matchmaker step, they have their window. Pair generator collect match request from users, and matchmaker collect scoring result from each score microservices and make match results. We think that streaming is a natural solution to our problems, collecting our users and put them in the window where they wait for some time until the matches are done. We close the window and calculate who matches with whom and continue. It's a general stream cycle, so I think it fits streaming very well. Let's explain detailed implementation about each operator one by one. First part is about handling source. First, to collect the request from clients, we can receive requests from Kafka sources or request directly from HTTP clients. These two options have our pros and cons. Distributed message queues such as Kafka help ensure the stability of our streams and reduce dependencies between applications. Option 2 may be selected to improve response time closer to real time. At this time, we developed our custom HTTP server source referring to the net extension of Apache Jaehyeok project. The second step is feature processing. In this step, most of the data remains unchanged within the match cycle. Therefore, we want to process the data separately to be used for scoring from the match cycle. So, data had to be processed in advance before entering the cycle. The user's attributes in request source are converted to feature vector form for machine learning models, or some requests are tagged under certain conditions for A/B test. We will introduce about state manager for feature enrichment as extra parts, so I will skip it this time. Our special concern in feature engineering step is the separation of data to reduce communication cost between operators. Only a small portion of the feature attributes are changed in the actual matchmaking cycles. Thus, this matchmaking context information was pre-separated and sent to next operator directly, and the remaining large size of data were only broadcasted to actual score operators. Third, before we perform the score calculation of the matchmaking, we first receive the request to the pair generator that defines the pair set. The operator collects match requests using the Apache Flink window API. The window trigger and arbiter condition is based on a certain time interval, but can also be set arbitrarily depending on the matchmaking functions. An operator generates a pair protocol to be used for distributed processing based on requests in window. The method of generating pairs is defined by agreement with the score operators. Our pair protocol between generator and score microservices use pairwise map reduce algorithm with block approach. In this process, we try to use the best algorithm to efficiently reduce communication cost between operators. Communication costs include network time and serialization and deserialization processing time. To match the number of n requests, a score of n square pairs is required. If this pair operation is performed on a single node, the computation time of scoring is increased relative to n square. Therefore, with distributed data processing, we can optimize this operation using multiple parallel tasks with size of p, and then time complexity of pairwise computations will be reduced by the amount divided by p. However, if n request data are very large, the communication cost of the broadcast approach will increase proportionally to this size of n, because every node should know all request information, so it cannot reduce on parallel approach. Therefore, also in order to optimize the communication cost well, we can use the block approach method to define blocks and process requests in block units. In this case, we can reduce the total communication cost by ON divided by block size. Let's look at the figure 1. If we divide the block like this and send it to each operator don't need to know all of the number of N requests. They need to know just their block request. Next, perform the actual pair score operations. Matchmaking logic is divided into external microservices because there are several teams working on it. And there are various scoring microservices exist. Some scoring services are rule-based microservices that determine hard constraint and others common runners. Therefore, the operator prepares the data to be provided to the microservices and obtains a response from the microservice. When handling over the data to the operator, the context is separated from step 2 are directly delivered, but other data are passed through the broadcast operator method or through external in-memory cache, such as Redis. Various teams can develop microservices which can be used for scoring. Therefore, we consider that when designing the architecture, both the REST API method and the event stream method were possible for microservice. And we use the sync stream when receive the API's response. The next step is to select the best pair to match based on the score calculation result that based on score operators. First of all, we have to put together the scores that are delivered by microservices. We have implemented a new custom tree and evictor because the match cycle must be completed in a certain amount of time. We need to consider scenarios in which certain scores failed. The process of selecting the best pair also improved the performance by utilizing distributed sorting algorithm. For unselected match request, we used an iterative stream to deliver them back to the pair generator. Actual example code shown like this. We define each operators and windows are defined on generator and aggregator steps. In this example, we use a tumbling processing time window on generator step and define custom trigger and custom evictor with a global window on score aggregation step. If we divide the request with some segmentation condition, we can make use a keyed window on each operator. And after matchmaking step, this operator produces some leftovers through side output. So we can pass these leftovers to generator again using the iterative stream. And our trigger condition is shown above. A matchmaker's window trigger checks when every element arrives to ensure that all scores results of current cycle are collected. However, we cannot guarantee that the result of each operation will arrive within the time that we require. So we can complete the implementation of window aggregation by adding a dummy timeout to a trigger condition that indicates end time of current cycle. Secondly, we have one more thing to consider about the scenario in which the score operation fails. If the score operation fails, there will be more unmatched requests than before. These unmatched are forwarded back to the pair generation step for using in the next pair score operation. If the match cycle is repeated and the computations include the score calculation time will be more longer than previous cycle because of large computations. So score of failure will be accumulated. Therefore, we need to avoid this process at the application level. So we implement the application level backpressure. We have bypassed the problem by buffering random requests at the matchmaker operator. Finally, the selected best pair is delivered to various sync. We can pass the result to the broker performing the actual client-to-client video matching. or we can forward the distribution result of these matches to the feedback system that will allow us to better perform the next match. Or there are more functions like the data logging, reporting to handle match result. Next part, let me give you a quick explanation of how we manage the matchmaking system stably. We actually operate this Flink application in our production environments. In our services, all Flink nodes run on the Kubernetes. We implemented it in the form of a standalone job to use the path variable features of the Kubernetes job. Metrics were aggregated using Prometheus and Grafana. Since it is real-time data that should not have downtime, we have configured a deployment pipeline that can deploy on blue-green architecture. We also consider using the checkpointing function in Flink with message queue as a source, but we did not adopt it because we could not avoid the downtime of some seconds. We already implement the first tolerance system for scorers, so each score microservice can be rolling updated. I'm sure most of you know the basic performance tuning, but I will briefly introduce you to the functions that you need to set up with more care when developing applications that are aimed at high priority on low latency. For applications where latency is important than throughput, you should always pay close attention to the network cost between operators. So we adjust the buffer timeout to near zero so that the next operator could be performed quickly. And in addition, we properly set the parallelism between operators to minimize the data movement by reducing unnecessary rebalance. The pair generator, we needed to use task slot independently. In this case, we can use a slot sharing group function on each operator. Okay. And next part, the Jaehyeuk will continue the contents.
Thanks, Gihoon. Before introducing how we implemented stateful matchmaking, I want to clarify the meaning of stateful matchmaking. So what is stateful matchmaking? We define stateful matchmaking can be realized with the real-time state and real-time inference. With stateful matchmaking, we can solve the optimal experience catching up with the user's context. Real-time inference is implemented by metric calculation in Scorer, so I'm going to focus on state management in this session. There are 4 steps for state management in our system. For the first step, we convert the sources into the state snippets. There are various state sources, such as match request and result. Match request contains the user's preference and the user's characteristics, and result shows the peer's characteristics and the quality of the matching experience. We convert these sources into the state snippets and pass them to the state management pipelines. And there are 2 different kinds of pipelines, synchronized and asynchronous. Synchronized means that the state pipeline and operators are integrated directly with the matchmaking system. To meet the latency requirements, we can only complete our task with a synchronized pipeline. But we find that for handling longer window size, it's difficult to meet the latency goal. That's the main reason why we introduced the additional asynchronous pipeline to our system. With these 2 different kinds of pipelines together, we can calculate features having long window size and update it immediately. And the states are stored in Redis for sharing states between blue-green clusters for preparing the case of failover. And often, some states are fetched from the Redis as the initial states for resolving the cold start problem. And finally, for enriching the requests or scorer, you use states to extract the features. And I will now walk through an example. With this stateful matchmaking system, we can implement personalization with user state. Often, the user explores agile matching space for finding better users, better peers. But in the natural condition, there are many difficulties for exploring because the user's time has a limit, and if the favorable peer segments had a small population in the matching space, the matching possibility with the target peer is lower than other majorities. So we have the exploring user to match with the favorable groups more with the multi-unbounded algorithm as known as MAB. For MAB, we are keeping the user's favorable peer groups. And for solving the cold start problem, if there is no favorable peer group for users, we start from one of the user segment states. These cold starting states are fetched from Redis. And then real-time inference is implemented by a matrix calculation between the favorability vector of the request and the matchability matrix in Squirrel. With this system, we can serve the optimal experience for each user as possible. And to run this stateful matchmaking system stably, it's needed to take the balance between latency and the size of states. The size means the window length of each state and also the number of different kinds of states. Because almost all states having long lasting time in the system, and all the memory usage for the states tend to move to heap. So the states should be managed with TTL, and it causes garbage collection pressure to the system. Because all the garbage collection pressure turned out to be the performance loss, I focus to spread this pressure and trigger garbage collection frequently. For this purpose, I find that lower initiating heap occupancy percent and higher concurrent garbage collect threads are necessary, and also not to set disabled explicit garbage collection option. And if the traffic is raised and the created state snippet are increased, the garbage collection balance could be break, and the memory usage and the garbage collection latency could be also raised. So monitoring garbage collection count and memory usage are essential. Until now, we've explained why we choose Flink to migrate our matchmaking server and how can we achieve the stability and expandability with the framework. So we can realize stateful matchmaking based on this new matchmaking system. With this achievement, we could adapt multiple models to solve better quality of experience for our user. This is the end of the session. Thanks for listening.